Happy Thanksgiving, Math 116. This is Paul, starting out on page 6 of the Outline 8 notes with two more examples in this video of computing a conjugate convex functional and then recovering the original functional from it. This one is especially simple. I'm going to pick the function f equals 0 but restrict its domain, capital C, to be just the closed interval from 1 to 2. And let's start out with a graph of that function in the left-hand diagram, trying to construct the conjugate functional. Here's an easy graphical way to do it. First, let's think about the case where m is less than 0. If I draw a line whose slope is m less than 0, it lies entirely below the graph, and what I can do is slide that line up until it just touches the graph. Clearly it will touch the graph at the left end of the domain at x equals 1, and then I look at where that line intersects the vertical axis. That intercept is minus f star of m. And it's clear, since the line has a negative slope m, that f star of m is equal to minus m for negative m. On my graph of f star of m, I've shown that the graph is a line of slope 1 for negative m. Now let's try with a positive m. Here is a line of positive slope m. Other lines with positive slope m would lie entirely below the graph. If I slide such a line up, it first touches the graph at x equals 2, and the value of minus f star of m, shown as the intercept here, is clearly minus 2 times the slope m. That means that for positive m, the value of f star of m is 2m, and therefore the conjugate functional is a broken line graph of slope 1 for negative m, that's encoding one end of the domain, and slope 2 for positive m, that's encoding the other end of the domain. If I now try to reverse the process, I have to do the same thing working backwards from the graph of f star of m, and I will use the same approach. Let's first think about what happens if x is less than 1. Now in this case, since we have a function of m, the variable for the conjugate functional is going to be x. So x denotes the slope of the line, so we're thinking of a line whose slope is less than 1. Like this one. Slide it up till it just touches the graph. You can't do it. It cuts the graph no matter what. And what that means is that values of x that are less than 1 are not in the domain of the conjugate of f star. Another way of looking at that is to say what we're trying to do is to find the supremum of xm minus f star of m. That clearly gets bigger and bigger as m becomes more and more negative, so the supremum does not exist. A similar thing happens if I consider the case where the slope x is greater than 2. If the slope x is greater than 2 and I try to slide a line up, I can't get it below the graph in the first place. A line of slope greater than 2 will always intersect this graph, which means that values of x greater than 2 are not in the domain of the conjugate functional. Another way of looking at that, you can say, if I look at xm on such a line minus f star of m, that difference just gets bigger and bigger as m becomes more and more positive. The supremum doesn't exist. What if 1 is less than or equal to x is less than or equal to 2? Well, here is a line whose slope is between 1 and 2. This time we can actually get that line below the graph. We slide it up. It touches at the origin, and that tells us the supremum of the difference. The largest value of xm minus f star of m is 0, achieved at m equals 0. So what have we concluded? We've concluded that the conjugate to this functional exists only if c is in the open interval from 1 to 2. We've recovered the original domain, and on that domain the supremum was equal to 0, so the function is f of x equals 0. We got our original function back. Now here's an example in 2 dimensions, which is purely algebraic. When we're computing norms, we have to take absolute values first, and you're probably not accustomed to differentiating powers of absolute values. So let me teach you a new differentiation rule. We want to differentiate the function 1/3 times the cube of the absolute value of u. That's 1/3 times the sine of u times u cubed, and we can apply the product rule to that, as long as u is different from 0. If u is different from 0, then differentiating the 1/3 u cubed, we get 1/3 u squared, and multiply by the sine of u. If we differentiate the other term, the sine of u is constant whenever u is different from 0, so its derivative is 0, and we don't get a second term. And we've got the formula sine of u times u squared. That's not valid if u is equal to 0, but we can always go back to the definition of the derivative. That's the limit as u approaches 0 of the function value minus the value at 0 divided by u. Clearly we've got 3 powers of u upstairs, 1 downstairs, and that limit is 0. I proved this result for the special case of the cube, but this works for any exponent p that's greater than or equal to 1. Why did I do that? Because my f of x is 1/3 absolute of u cubed plus 1/3 absolute of v cubed, and so to compute the conjugate functional, which will be a function on the dual space with a functional in the dual space represented by a pair of coefficients a and b, I've got to compute the supremum over all of 2-dimensional space of au plus bv, the linear functional, minus f of x. How do I do that? Of course, I set the derivative equal to 0 with respect to both u and v, and using my new differentiation rule, I find, for example, that the supremum can only be achieved where a minus the sine of u times u squared is equal to 0. What does that tell me immediately? Well, u squared, of course, is positive, and that means that a has to have the same sign as u. If u is positive, the sine of u is positive, a has to be positive. If u is negative, its square is 0, but this quantity is negative, and a has to be negative. So that means that u is in magnitude the square root of the absolute value of a. A can be negative, but we're taking the square root of its absolute value, and then we slap on a sine of a to restore the absolute value. Now that we know where the supremum is, we can calculate its value. Au is a times the sine of a times absolute of a to the 1/2. But remember, a times the sine of a is just the absolute value of a. So we have absolute of a to the 3/2. U cubed is going to be the cube of this quantity, which is the absolute value of a to the 3/2. Exactly the same thing works with v and b. And when I put everything together, au plus bv is a to the 3/2 plus b to the 3/2. 1/3 absolute of u cubed is 1/3 absolute of a to the 3/2. 1/3 of absolute of v cubed is 1/3 of absolute of b to the 3/2. It always happens. You get two terms that are the same except for the coefficients, and on combining them, I've got my conjugate functional, 2/3 absolute of a to the 3/2 plus 2/3 absolute of b to the 3/2. What do you know? 1 over p plus 1 over q is equal to 1, and if I had done this with a different exponent greater than 1, I still would have got the corresponding q. Not only that, I started with a coefficient of 1 over p here and ended up with a coefficient of 1 over q here. It's clear that if I repeat this process, I'll change this 2/3 back into a 1/3. I will change this 3/2 power back into a 1/3 power, and I will recover f of u and v. Now let me derive a more general result of the same sort. This is a formula that really should have been mentioned in Leuenberger. Even, wait a minute, did I jump 2 pages? Oh, yes, I did. So let's try this. This is your proof 3.9. You've noticed in the examples that the conjugate functional to a convex functional turned out to be convex. This is true in general, and it's actually quite easy to prove. First, you've got to look at this strange definition. The domain C star of the conjugate functional is the subset in the dual space where the supremum of x star acting on x minus f of x actually exists. In other words, if this supremum doesn't exist because we can find arbitrarily large values of this difference in functions, then the point is not in C star. If this exists, then the supremum itself is the value of the conjugate functional x star. And the challenge is to prove that the domain is convex and that the functional is convex. Well, how do we prove that something is convex? To prove that a set is convex, we choose 2 points in the set. We choose an alpha in between 0 and 1, and we interpolate. So instead of using x star, we use alpha x1 star plus 1 minus alpha x2 star. I have to subtract off f of x, but I'm savvy enough to write that as alpha times f of x plus 1 minus alpha times f of x. Then I can combine the terms that have an alpha in them and get one supremum. I combine the terms that have a factor of 1 minus alpha and get another supremum. This one involves just x1 star. This involves just x2 star. And we know that x1 star is in the set C star, and therefore this supremum exists. For similar reasons, this supremum exists. And since the supremum of a sum is always less than the sum of the suprema, this exists, therefore this exists and is smaller, and we've proved that C star is convex. This is actually quite a useful result, even in the case that frequently arises where we're dealing with a C star that is just a subset of the real numbers. If a subset of the real numbers is convex, it has to be connected, because if it weren't connected, you could draw a segment that extended from one component into the other component, and in between there would be missing points. Now we set about proving that f star is convex. How do we show that a functional is convex? A functional is convex if the value at the interpolated point is less than or equal to the interpolated value. In other words, if f star evaluated at the interpolated point alpha times x1 star plus 1 minus alpha times x2 star is less than or equal to the interpolation alpha times f star evaluated at f1 plus 1 minus alpha times f star evaluated at x2. I can write out what this means, and what I see is that this inequality is exactly what I proved above. So I've already done all the algebra, and if this shows up on the final exam, you can also comment, this is true because I did the algebra in the first part. That ends this theorem, and that ends this short video.